Okay, standard normal distributions, or in other words, the z distribution. Any distribution of normal distribution of data points, x values, can be transformed into a standard normal distribution by converting it to a z distribution by using this equation. So you take x minus the mean divided by the standard deviation. What that does is it transforms every normal distribution into a normal distribution where the mean is 0 and the standard deviation is 1. A z distribution has a mean of 0 and a standard deviation of 1. So it converts it to that so that everything is the same. There, we can compare any set of data to each other based on a z distribution or a standard normal distribution. And we can do that by saying that by substituting x in for z. Remember, this is our probability or probability density distribution function. If x is equal to z, the mean is equal to 0 and distribution is equal to 1, that function becomes this function just by substituting in. And then we can compare sets of data. So I could compare a math test to a science test. I could compare, different things to each other because I'm converting them to the same scale. All right. The cumulative distribution function is phi of a is equal to the probability of z less than or equal to that a value. And that is phi, P-H-I. That's the Greek letter phi. Anytime you see phi, that means you're doing a probability or a z distribution. Since z is continuous, when z is less than a, the probability of z being less than a is equal to the probability of z less than a, less than or equal to a, is equal to phi of a. So we do this calculation, and this is really what we're trying to find. We're trying to find the area under that curve at that point. And we do it by using tables of values. And those tables of values are given to you in your formula packet, and they're also given in the book, and they're also here on the next couple of pages. But we're trying to find it, and since it's always the same, we don't have to calculate it every time. It's just that's the way it is. So, and yes, you can do it in your calculator. If I want to find the other half, let's just say I wanted to find the probability density of this piece over here, I would simply go 1 minus the probability that's less than that. So I can still find when it's greater than. So if it does say that it's greater than, I can do that by taking 1 minus whatever the probability is that's less than that same value. So it's not an issue. We can still calculate when it's greater than. Here's a table, and what this means, the second decimal place. So here's the first decimal place along the vertical column. This is the vertical decimal place. And then over here, this is the second decimal place, and we can map it out all the way. So, and typically you're not going to be doing calculations that are more than 2.39 standard deviations away. So you don't have to worry about that. The table will be able to cover everything we need to do. Going on, so here's an example. If z is a standard normal variable without using technology, so in other words, using the table, what's the probability that z is less than 1.5? Probability of z is less than 1.5, just using a table. Okay, I don't have to convert it to a z value, it's already in z form, which we'll talk about next. But all I'm doing here is actually just demonstrating how to use the table. So probability of z is less than 1.5. So I go back to my table, 1.5. Here's 1.5. There's the probability because it's the 0. The second digit is 0. So it's 0.933. So this answer is 0.933. 9332, whatever. Now, for the next one, probability of z is greater than 0.84. Since it says greater than, I have to go 1 minus the probability of z being greater than 0.84. Okay. So I do that by going to my table, 0.84. So I'm 0.84, there's 0.84. So I go to 0.804, 0.7995. So it's 1 minus 0.7995. And from there, that's about point, 2005. Okay. All right, then lastly, the probability of a negative 0.41 is less than z is less than 0.67. What would I need to do for this one? So what I need to do for this one, I'm not going to do all the calculations, but I'm looking for a distribution from negative 0.41 to 0.67. So really what I have to do is I have to take the upper bound, the upper limit, minus the lower one. So the probability that z is less than 0.67, and to do that I have to use the formula, minus the probability of z is greater than negative 0.41. This over a little bit further. Right? And just doing those calculations, just by simply doing those calculations, getting the values from the table, less than 0.67. If I go to 0.67 back on the table, 0.67 is, let's see, 0.7486, okay, 0.7486 minus 0.309, so the distribution or the amount of data that's in between is 0.40. So it's just using numbers from the table. Okay? All right, let's continue. Interpreting what those z values mean. Well, if x is an observation of a normal distribution with a mean of mu and a standard deviation of sigma, the z-score of x is the number of standard deviations x is from the mean. It's the number of, when it's converted to a z-score, it's how far the x, it's the number of standard deviations x is from the mean. So if for example, z1 is 1.84, then z1 is the data point z1 is 1.84 standard deviations to the right of the mean, or if it's negative, it's 0.27 from the, to the left of the mean if it's negative. So in other words, example, Kelly scored 73% in history where the class mean was 68% and the standard deviation was 10.2. In mathematics, she scored 66% and the class mean was 62%. Standard deviation was 6.8. In which subject did Kelly perform better compared to the rest of her class? Assume the scores for both subjects were normally distributed. So what we want to do to be able to compare these two things, because they're history and math, we convert them both to z-scores. So let's do math and history. So working with her history score, we can convert her history score, or her math score, either one, into a z-score. So we're going to take the score itself. She scored a 66 minus the mean divided by the standard deviation. And we're going to do the same for history. She scored a 73 minus the mean divided by the standard deviation. And in doing so, for history, we find that it's 0.49, and for math, we find that it's 0.588. Well, what does that mean? Well, that means it's Kelly's result in math was 0.588 standard deviations above the mean. So this is 0.588 above the mean. And that means that this one's 0.49 above the mean. So where was she more above the mean? Where did she do better comparatively to the rest of the class? She actually did better in math because she was farther from the mean. She was above the mean greater by a greater amount. That's really what it means. That's what a z-score can do. It allows you to compare to each other. All right, going on to standardizing any normal distribution. First thing you're going to do is convert the x values to z values by using that formula, x minus the mean divided by the standard deviation. Sketch a standard normal curve and shade the required region, and then use the standard normal tables or a graphics calculator to find the probability. And I'm not showing you on the calculator, I'm simply showing you on the tables because you can use the tables all the time anyway. So here, I need to convert this because it's not in Z form yet. I need to convert this into, step one, I need to convert it into a Z-score. So I need to convert Z is equal to 69 minus the mean, 62, divided by the standard deviation of 7. So that is, Z is 1, 7 over 7. Okay. Then, from there, I just want to convert those. So I rewrite that into Z form, probability that Z is less than 1, less than or equal to 1. And then I can go to my table. If I go to my table, Z is 1, 0.8413. So it's 0.8413 is the standard deviation, or not the standard deviation, the Z-score. Okay, that's the percentage. What does that mean? 84% of the data, 84.13% of the data is less than 60, or is 69 or less. Is 69 or less. Is 69 or less. For the next one, I need to convert both of those into Z-scores. So I do the same process. I can step number one, I convert them to Z-scores. No, I didn't do the graph of this, sketching the graph of this. But when Z is 1, my standard deviation, here's my mean, my 1 standard deviation, I should know if Z is 1. That means it's 1 standard deviation away. And we know that based on a normal curve. Okay, anyway, I do the same for this other one, and what I wind up with is I wind up with P, the probability of negative 0.5 less than or equal to Z is less than or equal to 1.4. Okay. So what I have to do, I could do the sketch of this. If I do a sketch of this, here's that, that's the mean. So I'm going to be negative 0.5 to 1.4. And I'm going to find the area in there. So I'm going to use the probability of Z is less than or equal to 1.4 minus the probability of Z is less than or equal to negative 0.5. And just subtract those, and in doing so I get 0.9192 from the table is all I'm doing, minus 1 minus 0.6915, which comes out to be 0.611. That means 61% of the data is between 58.5 and 71.8. Okay. 61.1% of the data is between those. That's really all it's telling us. Okay. And I'm doing it using tables. Every calculator is different, so you could learn how to use it on the calculator as well. See you tomorrow. Have a great day.